Welcome! In this session, we will explore the problem maximum score after splitting a string. We'll walk through the problem requirements, analyze potential approaches, and break down the solution step by step. Let's get started. The problem asks us to work with a binary string, which is a string made up of only the characters 0 and 1. Our task is to split this string into two non-empty substrings, which we will call left and right. The goal here is to maximize the score of such a split. Now, the score of a split is calculated as the number of 0 characters present in the left substring, added to the number of 1 characters found in the right substring. The challenge is to determine what is the maximum score we can achieve by splitting the string in all possible ways. For input, we are given a binary string s, and the output will be an integer representing this maximum score. For instance, let's consider the example where the input string is 011101. The output for this case is 5. To understand why, let's look at the possible splits of the string. If we split it as 011,101, the score is the number of zeros in left, which is 1, plus the number of ones in right, which is 3, giving a total score of 4. Similarly, if we split it as 011101 foot, the score is also 4. When we split it as 011,101, the score becomes 1 from the zeros in left and 2 from the ones in right, giving 3. Another split, 011101, results in a score of 2, and for 011101, the score is 3. Among all these options, the maximum score is 5, achieved by the split 011,101. Another example is 00111, where the maximum score is also 5, as we'll examine in detail next. Now, let's break down the example 00111 further. When we split it as 00111, the score is 1 from the zeros in left and 3 from the ones in right, giving a total score of 4. Splitting it as 2111 foot gives a score of 2 from left and 3 from right, which sums up to 5. Another split, 00111, results in a score of 4, and splitting it as 00111 gives a score of 3. So, the maximum score of 5 is achieved by the split 2111 foot. For a different example, consider 1111. Here, the maximum score is 3. Let's examine how this score is calculated. In the case of 1111, the splits are as follows: 111 gives a score of 0 from the zeros in left and 3 from the ones in right, resulting in a total score of 3. For the split 1111 foot, the score is 0 plus 2, which equals 2. Lastly, splitting as 111 results in a score of 1. The maximum score here is 3, achieved by the split 111. Finally, we must keep in mind several constraints and edge cases. The string length ranges from 2 to 500, and each character is either 0 or 1. Importantly, the string must have at least 1 0 and 1 1. For edge cases, we need to handle the smallest string lengths, such as 01 foot, which has only one valid split, as well as strings with uneven distributions of zeros and ones, ensuring all splits are considered to determine the maximum score. To tackle this problem, the brute force approach is the most intuitive starting point. Here, we examine each possible way to split the binary string into two substrings, one on the left and one on the right. For every split, we calculate the number of zeros in the left substring and the number of ones in the right substring. The score for that split is simply the sum of these two counts. As we iterate through all possible splits, we keep track of the maximum score encountered. While this approach is straightforward, it has a significant drawback. For each split, we must recount the zeros and ones, which leads to a time complexity of O(n) per split. Since there are n1 possible splits, the overall complexity becomes O(n) squared. This is inefficient for larger strings, especially when the length of the string grows into the tens or hundreds of thousands. While the space usage is minimal at O(1), this method is not scalable due to its high computational demands. A more efficient approach leverages the prefix sum technique to pre-compute useful information, avoiding redundant recalculations. In this method, we first traverse the string to compute a cumulative count of zeros for each position, which we store in an array called prefix_zeros. This array allows us to instantly retrieve the number of zeros in the left substring for any split. Similarly, we calculate the total number of ones in the string. For a given split point, the the ones in the right substring can be derived by subtracting the cumulative count of ones up to that point from the total count. Using these pre-computed values, we can quickly calculate the score for each split. This approach reduces the time complexity to O(n), as we only need 2 passes, one for building the prefix sum and another for evaluating the splits. However, it requires additional space to store the prefix sums, leading to a space complexity of O(n). While more efficient than brute force, this method can still be optimized further, particularly in terms of space usage. The single-pass optimized approach takes the idea of efficiency a step further by eliminating the need for additional space. Instead of pre-computing and storing prefix sums, we dynamically update the relevant counts as we traverse the string. As we iterate through the string, we maintain a running count of the zeros seen so far in the left substring and the remaining ones in the right substring. For each character in the string, if it's a 0, we increment the count of left_zeros. If it's a 1, we decrement the count of right_ones. The score for the current split is simply the sum of left_zeros and right_ones. By updating these counts dynamically, we can calculate the score for each split in constant time, making the entire process run in O(n) time. Additionally, this approach requires only a few scalar variables, so the space complexity is reduced to O(1). This method is not only efficient but also easy to implement, making it an ideal solution for this problem. Among the approaches considered, the single-pass optimized approach stands out as the best option due to its simplicity and efficiency. While the prefix sum method also achieves a linear time complexity, it requires additional memory to store the prefix arrays. The brute force approach, on the other hand, is too slow for larger inputs due to its quadratic time complexity. The key insight that makes the single-pass approach so effective is that the score of any split depends only on the counts of zeros in the left substring and ones in the right substring. This observation eliminates the need to explicitly split the string or pre-compute prefix arrays. By dynamically updating these counts as we traverse the string, we can compute the score for each split in constant time. This strategy balances both time and space efficiency, making it ideal for competitive programming scenarios where performance is critical. The trade-offs are clear. While brute force is simple, it's computationally expensive, and while the prefix sum method balances time and space, it still uses more memory than necessary. The single-pass approach avoids both of these drawbacks. In conclusion, the single-pass optimized approach is the most practical solution for this problem. It achieves linear time complexity, which ensures it can handle even the largest input sizes efficiently. Additionally, its constant space usage minimizes memory overhead, making it suitable for constrained environments. The method is not only computationally efficient but also straightforward to implement, which is particularly valuable in competitive programming or interview settings. By dynamically updating the counts of zeros and ones during a single traversal, we avoid the inefficiencies of the brute force and prefix sum methods while maintaining clarity and simplicity. This balance of speed, space efficiency, and simplicity makes the single-pass optimized approach the clear choice for solving this problem effectively. The goal of this problem is to split a binary string S into 2 non-empty substrings, left and right, in such a way that the score is maximized. The score is defined as the sum of the number of zeros in the left substring and the number of ones in the right substring. To begin, we need to validate the input. First, ensure that the string S is non-empty and contains only 0 and 1 characters. If the string length is less than 2, we cannot create 2 non-empty substrings, so we would return 0 or handle the input appropriately. This step ensures our algorithm has valid data to work with before proceeding further. Next, we pre-compute values to make score calculations efficient. Specifically, we use 2 arrays, left_zeros and right_ones. The left_zeros array will store the cumulative count of zeros from the start of the string up to each index. Similarly, the right_ones array will store the cumulative count of ones from each index to the end of the string. To build these arrays, we traverse the string twice. First, we traverse from left to right to populate left_zeros. At each index, if the character is 0, we increment the cumulative count from the previous index. Then, we traverse from right to left to populate right_ones. At each index, if the character is 1, we increment the cumulative count from the next index. Once these arrays are built, we iterate through all valid split points from index 1 to n1 to calculate the score at each split. The score for a split point I is simply the sum of left underscore zeros, I, and right underscore ones, I. Throughout this process, we track the maximum score encountered using a variable. After evaluating all split points, we return this maximum score. There are a few key insights that make this approach efficient. By pre-computing cumulative counts in the left underscore zeros and right underscore ones arrays, we eliminate the need to repeatedly calculate the counts for each split point, reducing redundant operations. This optimization allows us to compute the score in constant time for each split point. Additionally, we must handle edge cases, such as strings consisting entirely of zeros or ones. Correct initialization of the arrays ensures the algorithm handles these scenarios without errors. For strings with a minimum length of 2 characters, it's essential to ensure the split point logic maintains valid non-empty substrings. The algorithm uses cumulative arrays, which require O, N, space, and a single variable max underscore score to track the highest score. The key operations include O, N, initialization of the arrays through 2 traversals of the string and O, 1, score calculation for each split point. Overall, the algorithm achieves a time complexity of O, N, with a space complexity of O, N. Finally, while the algorithm is already efficient with its linear time complexity, we can further optimize its space usage. Instead of creating and storing the left underscore zeros and right underscore ones arrays, we can calculate the cumulative counts on the fly as we iterate through the string. By maintaining running totals for the left zeros and right ones, we eliminate the need for additional arrays, reducing the space complexity from O, N, to O, 1. This optimization is particularly useful for very large input strings, as it minimizes memory usage while maintaining the same linear time complexity. This implementation solves LeetCode problem number 1422, maximum score after splitting a string. The goal is to find the maximum score obtained by splitting the binary string S into 2 non-empty parts, where the score is calculated as the sum of the number of zeros in the left part and the number of ones in the right part. The solution follows these steps. 1. Variable initialization. We calculate the total number of ones in the string, right underscore ones, initially, which corresponds to all characters being considered part of the right substring. We also initialize left underscore zeros to 0 as no characters are in the left substring at the start. The max underscore score variable is initialized to 0. 2. Iterate through the string. Using a for loop, we traverse the string from the first character to the second to last character. This ensures that both the left and right substrings remain non-empty. 3. Update counts for each character. If it is 0, it gets added to the left substring, so left underscore zeros is increment. If it is 1, it shifts from the right substring to the left, so right underscore ones is decrement. 4. Calculate the score. The score for the current split is the sum of left underscore zeros and right underscore ones. We update max underscore score to be the maximum of its current value and the calculated score. 5. Return the result. After iterating through all possible splits, the function returns max underscore score as the maximum score obtainable. This solution is efficient with a time complexity of O, N, where N is the length of the string. The traversal of the string and the count operation are both linear, ensuring optimal performance. The implementation avoids unnecessary computations and handles all edge cases, such as strings with only zeros or ones, by ensuring both substrings remain non-empty. Here, we begin the Java implementation of the solution. The method maxScore takes a string S as input and calculates the maximum score that can be achieved by splitting the string into 2 non-empty parts. We start by determining the length of the string and initializing the maxScore variable to 0. Additionally, we set up 2 counters, left zeros to track the number of zeros in the left part of the split, and right ones to track the number of ones in the right part. To initialize right ones, we iterate through the entire string and count all the ones, as initially, the entire string is considered the right part. This ensures we have the correct starting count of ones before we begin iterating to split the string. Next, we iterate over the string up to the second to last character, since the right part cannot be empty. During this iteration, we update the left zeros count if the current character is a 0, and decrement the right ones count if the current character is a 1, as we are effectively moving characters from the right part to the left. Finally, we calculate the score for the current split by adding left zeros and right ones, and update max score to ensure it holds the maximum score encountered so far. The method concludes by returning the max score, which represents the highest score achievable by splitting the string into two non-empty parts. This approach ensures that we efficiently compute the result in a single pass through the string after the initial counting of ones, making the solution both concise and performant. In this example, we are given the string s equals 011101. First, we initialize some variables. The length of the string, n, is 6. We set max_score to 0, which will store the highest score we calculate. We also set left_zeros to 0, as initially, there are no zeros in the left partition. Finally, we count the total number of ones in the string, which is 4, and store this in right_ones. Now, we start iterating over the string. At index I equals 0, the character is 0, so we increment left_zeros to 1. The score at this step is the sum of left_zeros and right_ones, which equals 5. We update max_score to 5 since it's higher than the previous value. At index I equals 1, the character is 1, so we decrement right_ones to 3. The score here is 4, and since it's less than max_score, we don't update it. At index I equals 2, the character is again 1, so right_ones is reduced to 2, and the score is 3, which is still less than max_score. At index I equals 3, the character is 1, so we again decrement right_ones, which becomes 1. The score at this step is 2, and max_score remains 5. When we reach index I equals 4, the character is 0, so we increment left_zeros to 2. The score for this step is the sum of left_zeros and right_ones, which equals 3. However, this is still less than the current max_score of 5, so no update is made. Finally, after completing the iteration, the maximum score we achieve by splitting the string is 5. This becomes our output for this example. Now, let's look at another example where the input string is s equals 00. We start by initializing the variables. The length of the string, n, is 2. We set max_score to 0, left_zeros to 0, and count the total number of ones in the string. Since there are no ones, right_ones is initialized to 0. Next, we begin iterating. At index I equals 0, the character is 0, so we increment left_zeros to 1. The score at this point is the sum of left_zeros and right_ones, which equals 1. We update max_score to 1 since it's greater than the previous value of 0. After finishing the iteration, the maximum score for this example is 1. In this example, the input string is s equals 1111. We start by initializing the variables. The length of the string, n, is 4. We set max_score to 0, left_zeros to 0, and count the total number of ones in the string, which is 4. Thus, right_ones is initialized to 4. Now, we begin iterating over the string. At index I equals 0, the character is 1, so we decrement right_ones to 3. The score here is the sum of left_zeros and right_ones, which equals 3. We update max_score to 3 because it is higher than the previous value. At index I equals 1, the character is also 1, so right_ones decreases to 2. The score at this step is 2, which is less than max_score, so no update is made. At index I equals 2, the character is again 1, and right_ones becomes 1. At index I equals 2, the score is calculated as the sum of left_zeros and right_ones, which equals 1. However, this is less than the current max_score of 3, so no update is made. After completing the iteration, the maximum score remains 3. This is the final result for this example, as no partition of the string produces a higher score. Here, we analyze the time complexity of our optimized solution. The first operation involves counting the total number of ones in the string using the s.count1 method. This requires a single pass through the string, making it an O(n) operation, where n is the length of the input string. Next, we have the iteration through the string using a for loop, which runs from the first character up to the second to last character, resulting in n1 iterations. During each iteration, we either increment left_zeros or decrement right_ones, both of which are constant time operations. Additionally, calculating the score for the current split involves adding left underscore zeros and right underscore ones and comparing it with the current max underscore score, which are also O1 operations. Since all of these actions, including the loop itself, occur within a single traversal of the string, the overall time complexity of the loop is O(n). To determine the total time complexity of the solution, we combine the complexity of both major steps. The first step, counting ones, contributes O(n), and the second step, iterating through the string, also contributes O(n). When combined, the overall time complexity remains O(n), as the two O(n) terms add up linearly. Now, shifting to space complexity, the solution requires a constant amount of extra memory, regardless of the length of the input string. While the input string itself occupies O(n) space, this is provided externally and does not count as additional space used by the algorithm. The only extra memory used is for auxiliary variables, such as max underscore score, left underscore zeros, right underscore ones, and the loop index I. Since each of these is a scalar, they each require O(1) space. This ensures that the total space complexity of the algorithm is O(1). With no additional data structures or memory allocations, the overall space complexity remains O(1). Now, let's compare this optimized approach with a brute force solution. In a naive method, we would generate all possible splits of the string, which would involve n1 split points. For each split, we'd count the zeros in the left part and the ones in the right part. In the worst case, these counting operations would take O(n) for each split. Since there are n1 splits, this results in an overall time complexity of O(n) asterisk O(n) equals O(n) squared. By contrast, the optimized solution avoids these redundant calculations. It pre-computes the total count of ones in a single O(n) operation and then uses a single traversal of the string to maintain running totals of left underscore zeros and right underscore ones. This allows the score for each split to be calculated in O(1) per iteration, reducing the total time complexity to O(n). In terms of best, average, and worst cases, the runtime of the algorithm remains O(n) for all scenarios. This is because the algorithm always performs exactly two passes through the string, one for counting ones and another for iterating through the string to calculate split scores. Similarly, the space complexity remains O(1) in all cases, as the algorithm does not use any additional memory beyond a few scalar variables. To mathematically validate the O(n) time complexity, we note that the two main operations, counting ones and iterating through the string, each contribute O(n), and their combination remains O(n). For space complexity, the reliance on constant memory for auxiliary variables confirms an O(1) usage. By eliminating the redundant calculations present in the brute force approach and instead utilizing a single traversal with simple accumulators, the optimized solution achieves significant improvements in efficiency, making it both time and space optimal. When tackling this problem, it's important to be aware of common mistakes that can lead to incorrect or inefficient solutions. One such mistake is ignoring edge cases. For example, consider a string that is entirely made up of ones or zeros, or even an empty string. These scenarios can easily slip through if your solution assumes the existence of both zeros and ones. Testing for edge cases like strings of length 1 or uniform characters is critical to ensure your solution is robust. Another frequent error involves the incorrect counting of characters within substrings. Off by one errors, especially when managing indices for the split, can lead to subtle bugs. To avoid this, define clear boundaries for the left and right substrings and validate your logic with multiple test cases. Performance optimization is another area where mistakes occur. A brute force approach that evaluates every possible split might seem intuitive but can result in O(n) squared complexity, which is impractical for larger inputs. Instead, you should aim to use prefix sums to compute counts efficiently. Lastly, assuming fixed split points, such as dividing the string into equal halves, can lead to missed solutions, as the problem allows for splits at any index. Always ensure your logic aligns with the problem's flexibility. Another common issue arises from misinterpreting the problem statement itself. Some solutions focus solely on maximizing the score of one side of the split, neglecting the need to consider the combined score of both sides. This kind of partial understanding often results in incomplete solutions. To succeed in interviews, it's crucial to identify patterns in the problem. In this case, recognizing that prefix sums or cumulative counts are central to an optimized approach can save time and prevent unnecessary complexity. While brute force might be your initial thought process, it's essential to explain why you transition to a more efficient method, such as using prefix sums. Clear communication is another vital skill in interviews. For example, articulate how your solution accounts for edge cases, as interviewers often assess how thoroughly you've considered special scenarios. Additionally, always highlight the time complexity of your solution. If you've optimized from something like O(n) squared to O(n), explain why this improvement matters and how it's achieved. These steps not only demonstrate technical competence but also show that you understand the trade-offs involved in problem solving. To broaden your understanding of this problem's techniques, it's helpful to explore related problems that share similar patterns. For instance, LeetCode 1248, which involves counting the number of nice subarrays, utilizes prefix sums and counting strategies to solve the problem efficiently. Another example is LeetCode 560, where you calculate the number of subarrays that sum to a given value, again relying on cumulative sum techniques. LeetCode 1493, which focuses on finding the longest subarray of ones after deleting one element, introduces sliding window strategies and dynamic subarray manipulation. Finally, LeetCode 1013, which involves partitioning an array into 3 parts with equal sums, challenges you to partition arrays based on specific conditions, building on the skills of breaking down and analyzing subarrays. These problems not only reinforce concepts like prefix sums and sliding windows but also help you recognize recurring patterns, deepening your problem-solving toolkit. There are several alternative approaches you can consider when solving this problem. The first is using prefix sums. By pre-computing the cumulative count of zeros and ones up to each index, you can quickly determine the counts for any substring. This method reduces the time complexity to O(n), making it highly efficient, though it does require additional space to store the prefix sums. Another option is the sliding window approach, where you dynamically adjust the window as you iterate through the string. This method is particularly space-efficient and works well when dealing with dynamic subarray constraints, although it may be trickier to implement in cases with complex splitting conditions. Lastly, the two-pass solution involves one pass to gather global counts of zeros and ones, followed by a second pass to determine the optimal split point. This approach is easier to implement than sliding windows but is slightly less efficient compared to single-pass methods. Each of these techniques has its pros and cons, so it's important to choose the one that best suits the problem's requirements and constraints. Great work! We've covered the key concepts behind solving maximum score after splitting a string. We learned how to approach this problem efficiently and discussed important takeaways. Don't forget to like, share, and subscribe for more helpful videos. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!